Hi, everyone. Thanks for coming at this late hour. We'll definitely make it very interesting, so make it worth your while. So today we're going to discuss network bottlenecks as part of big data and AI platforms. And what is it that we can do in terms of hardware acceleration on-premise, so what kind of technologies are available today, and what is available on the cloud that you can use as a turnkey solution. So to give an intro to this, so basically, most of you guys working on big data AI platforms, you are very aware of this infinite loop of trying to remove performance roadblocks and improve the overall utilization and job runtime. Now, with faster storage devices such as DRAM, NVMe, SSDs, and the stronger than ever processing power that is available today in different platforms, the traditional network can just not keep up with the I/O flow of this type. Usually, upgrading to higher wire speeds will not do the trick here. There are some more complex solutions that had to be used in order to actually utilize high-end networks. And this is where kind of a co-design hardware acceleration solution can be used in order to utilize the actual power that a compute cluster has. So this talk is kind of a continuing sequence of two previous talks that I made in previous Spark Summits. The first one was introducing the first standalone RDMA accelerated shuffle plugin called SparkRDMA. Second one was basically the first preview of running SparkRDMA shuffle engine on Azure HPC nodes, demonstrating 2.6x job speed up on cloud VMs. So this is basically the first time that this kind of hardware acceleration for shuffle is available in the cloud. So before we dive in on what technologies are available, let's first of all try to come up with a list of popular network bottlenecks that exist in the wild. So generally speaking about network bottlenecks, these are not always caused by lack of bandwidth. So network I/O imposes overhead on many system components, memory management, allocation, deallocation, and so on, memory copy, garbage collection, and of course, the tedious work of serializing compression and encryption. This translates to actual CPU cycles. And those cycles are not available for the actual job we're trying to do. We're wasting a lot of CPU cycles doing stuff that we don't really care about. So hardware acceleration is one way to reduce this kind of overhead and release some CPU cycles and actually use them for the job we're trying to do. And this way, we can allow better utilization of the compute and network hardware. So one example of a network bottleneck, which is very common in big data and AI platforms, is shuffle. So it's basically the most expensive non-storage network I/O operation in compute clusters. As we can see on the right here, this is an example of how a breakdown of high bench terasort job looks like on Spark. We can see that the shuffle read phase, where most of the data is being transferred over the network, takes more than 50% of the actual job runtime. So it makes a lot of sense that reducing this runtime, or maybe eliminating most of it, can reduce the total job runtime significantly. So this is a block-in massive movement of transient data that is a very significant portion of a job. So some acceleration opportunities that could be used here. So first of all, more efficient serving with reduced server-side logic can reduce the CPU overhead, and again, allow more CPU cycles for the actual compute job. Serialization, compression, and encryption could be offloaded, and again, reduce CPU load. Also, reduce I/O overhead and latency of the total transfers by employing more modern transport protocols. Another thing is distributed training. So distributed training creates a lot of model updates, which create massive network traffic. Now, model update frequency rises as GPUs get stronger. We can see here on the right that comparing the same compute cluster with different GPUs, comparing stronger and stronger GPUs, we can see that the total runtime stays about the same, although the actual GPU active time is reduced significantly. And this is usually because of other factors on the network, which are the bottleneck. It could be the network itself. It could be other factors on the cluster. Here we see that if we have inter-GPU communication, for example, using RDMA, or anything that is faster than what it is now, can tremendously reduce the job runtime, as well as lower latency on the network transport, which basically where all the model updates go on. And also collectives offloads, which we're going to discuss later in the slides. So storage, of course, is a network bottleneck. It's probably the most massive data movement in a big data AI cluster. So premium devices such as DRAM and flash, and we saw a bunch of talks today about other forms of faster storage, they provide access speeds that were never seen before. Now, we're doing a distributed work in this place. So the network becomes a factor here. So before that, storage was very slow, and it wasn't able to saturate a network. And right now, with these higher speed storage devices, we need a faster network that can also remove the overhead of being able to transfer this data from one machine to another. So of course, higher bandwidth is a good acceleration opportunity here. Reduced transport overhead to, again, get CPU cycles. And of course, operating system and CPU bypass, so that storage can have direct access to and from the network without having to go through the CPU. So let's see how we can handle all of these and how we can make those acceleration opportunities into actual solutions that we can use in order to mitigate those problems. So first of all, we have network speeds or bandwidth. So we have 1, 10, 25, 40, 100, and even 200 gigs network. But the thing is that faster network doesn't necessarily mean a faster runtime. We can see here on the right that the effect of network speed on a bunch of different big data workloads does not necessarily mean a job speed up. We see that the change from 1 gig to 10 gig is very significant in job runtime. It means that the other components in the system are able to saturate a 1 gig line very easily. But what happens next, even when we move to 10 gig and then to 40 gig, the difference is not that big. And the reason is that there are other factors in the system which are not working fast enough in order to saturate a 40 gig line. So the thing about big data and this kind of transfers is that many of those workloads consist of relatively short bursts of data. So there's no actual sustainable high throughput usually in these kind of systems. And this is why higher bandwidth will not always improve or have any effect on the runtime. Another type of technology that's getting more and more traction in this field as well is InfiniBand. So InfiniBand is the de facto standard in the HPC world. We can see on the right-hand side here, this diagram shows the top 500 supercomputers in interconnect performance share. Basically, we can see that 38% of the top 500 supercomputers use InfiniBand as an interconnect, whereas all of the other ones are a little bit less. So InfiniBand is available in FDR, which is 56 gig, EDR 100, and HDR, which is coming up on 200 gig. One of its pros are sub-microsecond latency, which is unheard of in the Ethernet world. Native support for RDMA, which we're going to discuss next. Hardware accelerated transport layer, basically all of the transport parameters of managing the packet sequences and so on is done by the hardware, whereas in Ethernet and TCP specifically, it's done by the operating system, and it takes a lot of CPU cycles. It is true SDN in the sense that standard fabric components are open sourced and are developed by many companies that contribute to them. And they're all cross-platform and can run on different devices. So it makes it very easy for customers to adjust those to their specific use cases. And it has native support for switch collective offloads, which we're going to discuss later. So a few words on RDMA. So RDMA is remote direct memory access. It basically lets you read and write from to remote memory locations. You can basically read and write from memory that is on a remote machine, same as you do on a local machine. And you can imagine how useful it can be. On the right side here, we can see the different flows comparing RDMA and the traditional socket pipeline. So let's say you have a buffer in your Java application. And on the socket interface, any kind of send or receive operation will have to context switch into the kernel so that the networking stack in the kernel can perform all of the necessary steps for this kind of transfer. And all of those context switches, they take time, of course, and they also involve usually some memory copies. So you have to copy memory from your user-level application to kernel-level buffers, and sometimes even copy another time for the copy into the network adapter buffers as well. Whereas in RDMA, you get direct user-level access to the actual hardware device. You don't have to go through the kernel in order to do send and receive operations, and that saves a lot of time. Also, you gain zero copy in the sense that whatever you write into your buffer is immediately accessible from the network adapter itself. So we get direct hardware interface, which bypasses the kernel and the TCP IP in the I/O path. Another thing is that flow control and reliability of the transport is offloaded in hardware, whereas in the traditional TCP stack, it's done on the OS. And one more thing, so RDMA is, at this point, is pretty mature technology. It's already supported on almost all mid-range to high-end network adapters on both InfiniBand and Ethernet. Another technology that can assist us in this is what's called NVIDIA GPUDirect. So GPUDirect basically gives you direct DMA access over PCIe from a GPU device to another PCIe device, for example, a network adapter. In that case, RDMA can be used to read and write data directly to and from GPU memory. It could be within the same machine, or it could be between GPUs on different remote nodes. It avoids the CPU overhead completely and also provides us with zero copy in the same fashion as explained in the Java application. We can see here on the right that with GPUDirect, the network adapter in this case, or it could be another kind of PCIe device, it gets direct access to the GPU memory address space. So it can access the blocks there directly without having to go through the main memory in the system and the CPU, which also requires copying data. SmartNIC is something that is becoming very popular. It usually involves a network adapter that has a FPGA or an ASIC integrated to it that is meant to perform specific offloads. The FPGA case usually involves more kind of a tailor-made accelerations, which are specific to whatever customer workload is. ASIC is a little bit less flexible, but it gives much better performance. So there's a kind of a pros and cons for either. Common use cases for this is accelerating serialization, compression, and encryption. This is more on the I/O side. And on the actual data, it can also do kind of a data massaging along the network pipeline, doing aggregation, sorting, group by, and reduce operations, and of course, many more. It could be deployed in several options. So usually it is deployed as kind of a pipeline, whereas you post data to be sent, and then all of the offloads will be done on the data as it goes into the network. Another option is what's called look-aside. This is more similar to how GPUs are used, where you post work into this kind of acceleration device, and you get an asynchronous response once the data was processed. Third option is what's called bump on the wire. Bump on the wire is more like having a network adapter and then a separate FPGA device or ASIC device that controls data that flows directly into the wire. Most commonly, it's used for security applications, let's say for implementing some kind of a firewall, ACL, and managing adversary attacks. In the same context, there's what's called smart switch. So smart switch basically introduces in-network processing. So right now, we only discussed processing that happens before the data gets into the network or after it leaves the network. And in the smart switch case, this is more about reduction of the data while it flows through the fabric. And the interesting thing about this is that it's done in wire speed, because we can't have the data being slowed down because the switch is doing some work on it. Two examples of this approach is the more generic one, which is, one example is the MPI switch collectives offloads. Example of an implementation for it is the Mellanox Sharp. It's basically a library that is able to reduce data as it flows through the switch, meaning that the endpoint will get the data in a different form, maybe reduced a little bit in size. And the nice thing about this is that it is opportunistic. It means that it doesn't stop or block if it can make any progress on the data. It will just accelerate as much as possible and just keep the flow going. Another example is more kind of a pair workload acceleration, which is done on programmable switches. One example of it is Barefoot to Fino. And there's a very interesting paper explaining how network accelerated query processing can easily accelerate the performance of a big data cluster. Last but not least, so NVMe over fabrics. So NVMe are basically SSDs that have a PCIe interface instead of the traditional SATA. So NVMe over fabrics is basically a network protocol for NVMe devices to communicate over the network more efficiently. So it uses RDMA to provide direct network adapter to disk access, again, without having to go through the CPU and the main memory. In this case, we can have a host which does not have a lot of memory, does not have a lot of CPU power, but it can still serve as kind of a storage node without having to, for most operation, you don't have to go through the main system. So the network adapter will fetch the appropriate blocks and will send them over the network. And this is the nicest thing about it, is that it completely bypasses the host. And the main gains are minimal latency differences between local and remote access. You can basically see that accessing remote blocks takes the same time as it is accessing the local disk. And with this, I'm going to turn to my friend here to continue.
Thanks, Yuval. I think that was a great overview of the recent technology advancements. Now let's see which of these technologies are available on the cloud and what their performance expectations are. So before that, let me quickly give you a brief overview of how Azure offer a bare metal experience on the cloud. So we made our design pillars or design choices on these three pillars: eliminate jitter completely, full network experience, and transparent exposure of hardware. So, I mean, jitter, you all know, this is one of the main causes for non-deterministic performance, also variability over different runs. And full network exposure experience, how that's important. Even though we have latest and greatest hardware, what's the point if that's not exposed to the customer? Also, exposure of the hardware, like here I mean the cores. So even though the cores are pinned in the VM, but what if the hypervisor changes onto a different core? So it becomes really not useful. So how we take care of these things? So on the new SKUs, one of the approaches that we took was to hold back a few cores for host, and we partition it using the min root and CPU groups that's available from the hypervisor to isolate host and VM completely, and so that the hypervisor does not impact the VM at all, and vice versa. So this is just a start. We also have some advanced like designs trying to eliminate it even at a deeper level. And full network experience, here is where SRIOV or single root IO virtualization comes into picture. So here with SRIOV, the hypervisor exposes the NIC as a virtual function to the VM, and it has exclusive access. The VM has exclusive access to the NIC. So with this, there is no hypervisor intervention, and all the features of the network interconnect it's offered to the VM, and this allows us to support all MPIs, and also the VMs can take advantage of hardware offload features that are exposed by the hardware. Another main one was we want to expose the same cores that the physical machine has, physical host has, to the VMs. So when a program running on the VM maps a process to a particular core, it's actually the same core back on the host itself. So with these, we really get a real bare metal experience on the cloud. And I'm so excited to show this slide. So these are the HB and HC, one of the latest Azure HPC offerings. The HB is based on AMD EPYC architecture, mainly focusing on high bandwidth intensive workloads, and HC compute intensive workloads. Core-wise, HB has 60 and the other one's 44, and memory bandwidth for HB is around 260 GB per second, and HC, we reach a core frequency of around 3 GB per second. Network, like I said, like you all mentioned, this is the 100 Gbps EDR InfiniBand, and it supports like native IB. By that, we offer all the greatest and latest MPIs over all different operating systems. We also expose hardware offload and hardware collectives, and this can be accessed through the various models, Azure CLI, command line interface, or template, or Azure Cycle Cloud, or any of the partner platforms as well. And let me give you a brief overview of what other Azure HPC SKUs are, or a few highlights. So with SRIOV going broad, all the Azure HPC SKUs will have native IB support. And we also have some driver SKU performance optimizations that are coming. And GPU-wise, one of the highlights that I want to show was the NDV2 series. These have 8 NVIDIA Tesla NVLink, Tesla NV100 connector over NVLink. and Intel Skylake with 672 GB memory. And we believe these are one of the excellent platforms for both AI and HPC workloads. And last but not the least, the Azure FPGA, these are in preview now. So these are based on a Brainwave project from MSR. So we can deploy your model to the FPGAs or reconfigure them as you need. And it currently supports a variety of models, and these are growing as well. And now let's take a deeper look at what the performance expectations are. So let me start with the MPI benchmarks and why I picked MPI, because it's a good platform to compare the different network technologies. So MPI is at the same level, and then it's implemented on different interconnects or different transports. So here we compare Ethernet, which is the Azure front-end network, which is 40 Gbps, and then IP over IB and RDMA, both 100 GB per second. So IP over IB, again, it goes goes through the kernel. So again, we have some overheads. So if you see the numbers for MPI latency, Ethernet, it's around like 60 or 70 microsecond. IP over IB, it's around 15 to 20 microseconds. And if you see RDMA, it's around 1.77 microsecond. And I'm so excited to say that these are one of the best MPI latency numbers that you'll see in public cloud. Some of our competitors, so the numbers are in the range of 15 microsecond. That's the expectation. And bandwidth-wise, we see it's around 12 GB per second, which translates to around like 96 GB per second. And whereas you see IP over IB, even though it's on the same transport, it's still not able to reach that a high bandwidth, because it's again, there are a lot of software overheads because it's going through the kernel. And Ethernet, again, the bandwidth is not high as expected. And the number that I mentioned, 1.75 or 1.77 microsecond, this is getting even better. We have some driver and skew performance optimizations that those are coming, and these numbers are going to get even better. And so now we got a good understanding of how or what the network performance expectations are. And so now let's take a look at how SparkRDMA, like Yuval mentioned in the previous slides, Spark is actually one of the best candidates or good candidates for RDMA, because it's doing an in-memory shuffle, and RDMA is a good candidate to expedite the data transfer there. So here we compare an on-prem RDMA cluster and on Azure Cloud with RDMA. So these are so here we can see that on-prem or on cloud, it gives around like 2.1x performance improvement, and it's visible on both cloud and on-prem. And here we are comparing with IP over IB. So even though it's a faster network, because of the software overheads, we are still not able to reach that gap. So that's the highlight, I would say. And SparkRDMA on Azure. So these are taken on the new HC cluster. So again, the setup is similar, but here we took a much larger experiment setup. So these are 16 data nodes, whereas the previous one was 8 nodes. And here we can see that the numbers got even better on this side. And even though these are not really apple-to-apple comparisons, just because the software versions have been changed and the data is allocated on, here it's on SSD, where it was on the previous experiment it was on memory. So minor differences are there, but overall the numbers are getting even better on the new SKUs. I'd also show some of the other big data middleware which are accelerated using RDMA. For example, this is OSU HDFS-RDMA. So here, again, the data communication is accelerated over RDMA. So this is, again, based on Hadoop 3.0. And compare for the different technologies, like different transport technologies, Ethernet, IP over IP, and RDMA. So here we can see a scaling, and the performance gain actually kind of remains the same, or even sometimes increases as we scale up. And here we also increase the packet size for this experiment, because on IP over IP and RDMA we got much improved performance results with with higher packet size. And this is Memcached on RDMA. So like Yuval mentioned, Spark is one of the good candidates for RDMA. So is Memcached. Memcached is actually a distributed cache where the clients go to server for a key value set or a get, and the clients identify the server using a hash function of the key. So here the clients can do a set using an RDMA write, or do a get using an RDMA read. So here it's kind of an absolute perfect fit for applying RDMA here. So here also, if you see the latency of Memcached set or get is in the range 5 or 6 microseconds. But on the other hand, you take a look at IP over IP, that's around like 60 or 50 microseconds. Like we can see magnitudes of performance improvement here, and even Ethernet, it's even higher. So even though it's on the same network, using RDMA can further improve your latency and bandwidth. So this is also one of the OSU RDMA big data projects, and the Memcached versions are 1.53 and libmemcached 1.018. And we also took some performance evaluations for Kafka-RDMA. And here we can see that the latencies are almost cut down by half when we switched over to RDMA. And the bandwidth, we got a good improvement on the bandwidth as well. Like I mentioned before, so OSU OSU Big Data Project, and we see really good performance improvements with this. And last, let me show the Horovod on Azure as well. So Horovod, I mean, the special thing about this is I really like Horovod because it can use MPI as a network transport. So all the goodness that or research that had been done past several years on MPI, now we can apply to the big data or AI, and Horovod is actually a good platform to execute that idea. So here, the scalability trend is really awesome here, and this is again on Azure HC, ranging from 2 node to 16 node. So when we compare the 1 node scalability efficiency calculations to 16 node, we could see even at 16 nodes, the scalability efficiency was around like 97%, which was really impressive. And the MPI here is OpenMPI, and underlying transport was UCX. And here we made use of the hardware accelerated collectives. So so with MPI, all those things come for free, which is really great. Great. And as cloud, we kind of opens up all the hardware features to all the big data or AI frameworks. So with this, let me hand over to Yuval.
All right, so let's wrap this up. So we've seen a bunch of nice numbers when introducing RDMA acceleration. The thing is that if we consider all of the technologies we've mentioned, most of them are still not available in the cloud. We've seen many talks today, specifically in the morning in the keynotes, saying that domain-specific accelerators are going to take over the next decade. So we expect this table to change significantly very quickly. Let's compare what's available today on major clouds. So in terms of network speeds, 100 gig is available on Azure and AWS. GCP, as far as I could find, at least, it's only 20 gig. InfiniBand is already available on Azure, as well as RDMA. There is a small subset of RDMA operations which is supported in AWS, but it's quite limited. GPUDirect is not supported with RDMA pretty much anywhere right now. It's only supported within the same host between different GPUs on AWS. We can see that the other technologies have not been picked up by major clouds. But again, we expect it to change very quickly. To finish up, a few takeaways. So you can find all the accelerated frameworks that we've discussed. SparkRDMA is available on GitHub. The high-performance big data benchmark suite and the actual implementation for Kafka, Hadoop, and all the stuff we mentioned from OSU is also available online. Horovod by Uber as well. And you can also find some more reference to the Azure instances we've featured here, the HPC, HB, and HC, and the NDV2 GPUs, as well as the FPGA instances. Thank you, everyone, for coming. Let's go for questions.